Assalamu alaikum. Let's begin lecture number 22 of CS317 Operating Systems. The chapter under discussion is file management, and we are using chapter number 12 of the William Stallings book. In the last lecture, we discussed functions on files. We explored file structure. We discussed operations on files. We understood file management system and explored its objectives, architecture, functions, and performance issues. We discussed file organization. We explored different types of file organization. Today we start the lecture with B trees, which are data structures for file management. The need for B trees. In the previous lecture, we used an index file to access individual records in a file or database. For a large file or database, a single sequential file ordered by the primary key does not provide for rapid access. To provide more efficient access, a structured index file is typically used. The simple structure is a two-level organization. This structure can then be extended to more than two levels, resulting in a tree structure. Unless some discipline is imposed on the construction of the tree index, it is likely to end up with an uneven or unbalanced structure with some short branches and some long branches, so that the time to search the index is uneven. Formal definition. A B tree is a tree structure with the following characteristics. The tree consists of a number of nodes and leaves. Each node contains at least one key which uniquely identifies a file record and more than one pointer to child nodes or leaves. The number of keys and pointers contained in a node may vary. The maximum number of keys is same for all nodes. The keys in a node are stored in increasing order. Each pointer points to the root of a subtree containing all nodes with keys greater than the key on the pointer's left but less than or equal to the key on the pointer's right. The rightmost pointer points to the root of the subtree containing all keys greater than any keys in the node. Thus, each node has one more pointer than keys. Mathematical definition. A B tree is characterized by its minimum degree D and satisfies the following properties. Every node has at most 2D minus 1 keys and 2D children or pointers. The root has at least one key and two children. Every node except for the root has at least D minus 1 keys and D pointers. As a result, each internal node except the root is at least half full or has at least D children. All leaves appear on the same level and contain no information. This can also be implemented such that each bottom level node contains null pointers. A non-leaf node with k pointers contains k-1 keys. Relationship among keys. Typically, a B tree has a relatively large branching factor, large number of children. This results in a tree of low height. The upper level has k-1 keys and k pointers and satisfies the following relationship. Key 1 is less than key 2, which is less than key k minus 1. If you look at the picture here, all the keys in subtree 1 are less than key 1. All the keys in subtree 2 are greater than key 1 and less than key 2. All the keys in subtree 3 are greater than key 2 and less than key 3. All the keys in subtree k minus 1 are greater than key k minus 2 and less than key k minus 1. And all the keys in subtree k are greater than key k minus 1. Searching in a B tree. To search for a key, you start at the root node. If the key you want is in the node, you are done. If not, you go down one level. There are three cases. The key you want is less than the smallest key in this node. Take the leftmost pointer down to the next level. The key you want is greater than the largest key in this node. Take the rightmost pointer down to the next level. The key you want is between the values of two adjacent keys in this node. Take the pointer between these keys down to the next level. For example, consider the tree in the figure. We want to search 84. At the root level, 84 is greater than 51. So you take the rightmost branch down to the next level. Here we have 71, which is less than 84, which is less than 88. So you take the pointer between 71 and 88 down to the next level, where the key 84 is found. Associated with this key is a pointer to the desired record. Trace the steps to search for 42 by yourself. Is it a successful search? Advantages of B trees. An advantage of this tree structure over other tree structures is that it is broad and shallow, so that the search terminates quickly. Furthermore, because it is balanced, all branches from root to leaf are of equal length. All searches are of equal length. Insertion in a B tree. Before and after each insertion, the B tree must maintain balance. Suppose we want to insert a key K. Search the tree for K. If K is not in the tree, then you have reached a node at the lowest level. Let this node be N. If N has fewer than 2d minus 1 keys, it has a space. Then you insert the key K into N in the proper sequence. If N is full, having 2d minus 1 keys, then split N around its median key into two new nodes with d minus 1 keys each and promote the median key M to the next higher level in a parent node P. If K is less than M, insert it into the left new node. Otherwise, insert it into the right new node. The original node N has been split into two nodes, one with d minus 1 keys and one with d keys. The median key M is inserted into a parent node P following the rules of step 3. Therefore, if P has space, M is inserted in it such that all keys of P are in increasing order. If P is already full, it must be split and its median key promoted to the next higher level. If the process of promotion reaches the root node and the root node is already full, then insertion again follows the rules of step 3. However, in this case, the median key becomes a new root node and the height of the tree increases by 1. Consider the tree shown here. D equals 3. A node can have a maximum of 2D, that is 6 pointers, and 2D minus 1, that is 5 keys. We want to insert 90 as a key in this tree. We start at the root. 90 is greater than 71, so we follow the rightmost pointer of the root downwards. The node has space. The right position for 90 is between 88 and 96. Finally, 90 is inserted in the node. We want to insert 45 as a key in this tree. We start at the root. 23 is less than 45, which is less than 51. So we follow the pointer of the root between 23 and 51 downwards. The node does not have space. It is broken into two nodes. The left node has 30 and 32 and the right node has 43 and 44. The median node 39 is promoted up between 23 and 51. The right position for 45 is after 44 in the right new node. We want to insert key equals 84 in this tree now. We start at the root. 84 is greater than 71, so we follow the rightmost pointer of the root downwards. The node does not have space. It is broken into two nodes. The left node has 73 and 85. The right node has 90 and 96. The median node 88 is to be promoted up to the right of 71, but there is no space in the root node. The root is broken into two nodes. The left node has 23 and 39. The right node has 61 and 71. The median node is promoted up. Now the node 88, which was to be inserted in the old root, is inserted after 71. The tree has increased in height. The right position for 84 is between 73 and 85 in the left new node. Finally, 84 is inserted in the node. Your homework is to construct a B tree adding the values that are shown over here. Start with a node containing the first key only. Then keep on inserting keys in the order of the question and use the values of D which have been given to you. Let us now talk about file directories. Contents. Associated with any file management system and collection of files is a file directory. The directory contains information about the files including attributes, location, and ownership. Much of this information is managed by the operating system. The directory is itself a file, accessible by various file management routines. Although some of the information in directories is available to users and applications, this is generally provided indirectly by system routines. Table 12.2 suggests the information typically stored in the directory for each file in the system. From the user's point of view, the directory provides a mapping between file names and the files themselves. Thus, each file entry includes the name of the file. Virtually all systems deal with different types of files and different file organizations, and this information is also provided. An important category of information about each file concerns its storage, including its location and size. In shared systems, it is also important to provide information that is used to control access to the file. Typically, one user is the owner of the file and may grant certain access privileges to other users. Finally, usage information is needed to manage the current use of the file and to record the history of its usage. Operations on a directory. Search. When an application references a file, the directory must be searched to find the entry corresponding to that file. Create file. When a new file is created, an entry must be added to the directory. Delete file. When a file is deleted, an entry must be removed from the directory. List directory. All or a portion of the directory may be requested. This request results in a listing of all files owned by the requesting user plus some of the attributes of each file, for example, type, access control information, usage information. Update directory. If a file attribute is stored in the directory, changing it requires a change in the corresponding directory entry. Structure. The way in which the information of a directory is stored differs widely among various systems. Some directory information may be stored in a header record associated with the file. This reduces directory size. A small directory can be kept in entirety in main memory, which improves speed. The simplest form of structure for a directory is that of a list of entries, one for each file. This structure could be kept in a simple sequential file with the name of the file serving as the key. In some earlier single user systems, this technique has been used. Analysis of the sequential file implementation of a directory. The simple list is not suited to supporting directory operations. In single user systems, the user may have many types of files which he may like to organize in some way. The sequential directory provides no help in organizing the files. The sequential directory forces the user to be careful not to use the same name for two different files. In a shared system, unique naming becomes a serious problem. It is difficult to conceal portions of the overall directory from users so everyone can view everyone else's files. Two-level scheme for directories. There is one directory for each user and a master directory. The master directory has an entry for each user directory providing address and access control information. Each user directory is a simple list of the files of that user. This arrangement means that names must be unique only within the collection of files of a single user. The file system can enforce access restriction on user directories. It provides users no help in structuring collections of files. Tree structure for directories. A more powerful and flexible approach, and one that is almost universally adopted, is the hierarchical or tree structure approach. There is a master directory which has in it a number of user directories. Each of these user directories in turn may have subdirectories and files as entries. This is true at any level. That is, at any level, a directory may consist of entries for subdirectories and or entries for files. Directory organization. The simplest approach is to store each directory as a sequential file. When directories contain a very large number of entries, sequential organization leads to unnecessary long search times. In that case, a hashed structure is preferred. Naming. Users must be able to refer to a file by a symbolic name. Each file in the system must have a unique name so that file references are unambiguous. But it is a burden on users to require they provide unique names, especially in a shared system. The use of a tree structured directory minimizes the difficulty in assigning unique names. Any file in the system can be located by following a path down from the root directory until the file is reached. The series of directory names culminating in the file name itself constitutes a path name for the file. If two files have the same names but their paths from the root are different, their path names become different. Let us talk a bit about path names. The slash is used to delimit names in the sequence. It is used to differentiate between two names. The name of the master directory is implicit because all paths start at that directory. So you don't need to mention the name of the master directory in every path name. It is perfectly acceptable to have several files with the same file name as long as they have unique path names, which is equivalent to saying that the same file name may be used in different directories. Now let us trace the path for file ABC, which you can see in the lower left corner. We start from the master directory, then we go to directory called user B, then we go to a directory called word, then we go to a directory called unit A, and then we reach file ABC. So the path name is slash user B slash word slash unit A slash ABC. Let us now trace the path from the master directory to the other file named ABC in this picture. We start from the master directory and then we go to the directory called user B. Then we go to the directory called raw and then we reach our file ABC. So the path name is slash user B slash draw slash ABC. Both files have the same name, but since they exist in different directories, their path names are different, and this is perfectly allowed. Working directory. It is awkward for a user to give the entire path name every time a reference is made to a file. Typically, an interactive user or a process has associated with it a current directory, often referred to as the working directory. Files are referenced relative to the working directory. For example, if the working directory for user B is Word, then the file in the lower left corner can be sufficiently identified by unit A slash ABC. Home directory. When an interactive user logs on or when a process is created, the default for the working directory is the user's home directory. During execution, the user can navigate up or down in the tree to change to a different working directory. Now we will talk about file sharing. Issues in multi-user systems. In a multi-user system, there is almost always a requirement for allowing files to be shared among a number of users. Two issues arise: access rights and the management of simultaneous access. Access rights. The file system should provide a flexible tool for allowing extensive file sharing among users. Users or groups of users are granted certain access rights to a file. The following access rights can be assigned to a user for a file: none, knowledge, execution, reading, appending, updating, changing protection, deletion. Now I will explain each of the access rights that I listed for you. None. The user does not even know of the file, much less access it. To enforce this restriction, the user is prohibited from reading the directory that includes this file. Knowledge. The user knows that the file exists and who the owner is. The user is able to request the owner for additional access rights. Execution. The user can load and execute a program but cannot copy it. Reading. The user can read the file, copy it, and execute it. Some systems are able to enforce a distinction between reading and copying. In this case, the contents of the file can be displayed to the reader, but the user cannot make a copy. Appending. The user can add data to the file, often only at the end, but cannot modify or delete any of the file's current contents. This right is useful in collecting data from a number of sources. Updating. The user can modify, delete, and add to the file's data. This normally includes writing the file initially or creating it, rewriting it completely or in part, and removing all or a portion of the data. Changing protection. The user can change the access rights granted to other users. This right is held only by the owner of the file. In some systems, the owner can extend this right to others. To prevent abuse of this mechanism, the owner is able to specify which rights can be changed by the holder of this right. Suppose that I created a file ABC. I am the owner of file ABC. I can grant access to this file to anybody else in the system. I grant you the changing protection right on this file. This means that now you can also grant access to the file ABC apart from me. You are not the owner of the file, but since I have extended this access right to you, you can also grant access to other users. Suppose that I want you to only grant the reading access to other users. So there are ways in which I can grant you the changing protection access right, but I can also limit the actions that you take or the rights that you grant. Deletion. The user can delete the file from the file system. Hierarchy of access rights. The access rights discussed constitute a hierarchy, with each right implying those that precede it. Thus, if a particular user is granted the updating right for a particular file, then that user is also granted the following rights: knowledge, execution, reading, and appending. Usually, the person who initially creates a file is its owner. The owner has all access rights and may grant rights to others. Access can be provided to different classes of users. It can be provided to a specific user, individual users who are designated by user ID, or to user groups, a set of users who are not individually defined. The system may have some way of keeping track of the membership of user groups, or access may be provided to all users who have access to this system. These are public files. Simultaneous access. When appending or updating access is granted on a file to more than one users, the operating system or file management system must enforce discipline. A brute force approach is to allow a user to lock the entire file when it is to be updated. A finer grain of control is to lock individual records during update. This allows multiple users to update different records in the same file simultaneously. Essentially, this is the reader's writer's problem. Issues of mutual exclusion and deadlock must be addressed in designing the shared access capability. We have already seen how mutual exclusion is implemented and how solutions for readers writers problem are provided. Deadlock is a topic which we will discuss in chapters to come. We now talk about record blocking. Here are some issues to consider. Records are the logical unit of a structured file. Blocks are the unit of input and output with secondary storage. For I/O to be performed, records must be organized as blocks. There are several issues to consider. Should blocks be of fixed or variable length? What should the relative size of a block be compared to the average record size? Fixed or variable sized blocks. On most systems, blocks are of fixed length. This simplifies I/O, buffer allocation in main memory, and organization of blocks on secondary storage. Size of a block. The larger the block, the more records that are passed in one I/O operation. If a file is being searched sequentially, large block size is an advantage because the number of I/O operations is reduced, speeding up processing. If records are being accessed randomly and no particular locality of reference is observed, larger blocks result in the unnecessary transfer of unused records. Larger blocks require larger I/O buffers, making buffer management difficult. Methods of blocking. Given the size of a block, there are three methods of blocking. Fixed blocking. Fixed length records are used and an integral number of records are stored in a block. There may be unused space at the end of each block. This is referred to as internal fragmentation. Variable length is spanned blocking. Variable length records are used and are packed into blocks with no unused space. Thus, some records must span two blocks, with the continuation indicated by a pointer to the successor block. Notice that there is no internal fragmentation. Variable length unspanned blocking. Variable length records are used without spanning. There is wasted space in most blocks because we can't use the remainder of a block if the next record is larger than the remaining unused space. Analysis of various blocking choices. Fixed blocking is the common mode for sequential files with fixed length records. Variable length span blocking is efficient for storage and does not limit the size of records. However, this technique is difficult to implement. Records that span two blocks require two I/O operations, and files are difficult to update regardless of the organization. Variable length unspanned blocking results in wasted space and limits record size to the size of a block. Blocking choices in virtual memory. In a virtual memory environment, it is desirable to make the page the basic unit of transfer. Pages are generally quite small. It is impractical to treat a page as a block for unspanned blocking. Accordingly, some systems combine multiple pages to create a larger block for file I/O purposes. This approach is used for vSAM files on IBM mainframes. So, what did we learn? We discussed B trees and related issues. We explored file directories and their issues. We discussed file sharing and things that we need to do for it. We understood record blocking, its types, and their consequences. In the end, let me remind you to do your homework, create the B tree that I asked you to make, read the book, note your questions on a piece of paper and keep it in front of you during the online session, and email your suggestions relevant to the content or quality of this lecture to me. Take care. Allah Hafiz.